Okay, so we're given this problem, find the local extreme values of this function. It's a cubic function. It looks like a simple function, but we want to find the extreme values or the local extreme values. And the only way to do that we know right now is the first derivative test. The first derivative test. Since this function is actually defined for all values of x, we're only going to be looking at the interior points. If I draw an arbitrary cubic graph, notice that there's a couple things that I can point out. First off, that there is a local max and a local min here, and we can actually generalize how to find the local max or the local min by looking at the first derivative, because the first derivative gives you slope. And with slope, we're actually concerned with the sign of the slope, or positive or negative. Is it positive slope or is it negative slope? Notice that this goes to positive until you reach the critical point, and it goes to negative. If that's the case, from positive to negative, we call this a local max. And then similarly, the opposite, minus minus minus, reach the critical point, plus plus plus. This is a local min. And then there are cases where neither happens, like this one, where this is the critical point right in the middle, but it goes from positive, 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 hits the critical point, positive, positive, positive. This is neither. And we have to actually check if it's one of these three, local max, local min, or neither. But the first step always with finding extreme values is actually just finding the derivative, so let's do that. Power rule, right? Easy. That's always the easiest step actually now, just using the power rule. Now we have to find critical points. And how do we find critical points? Remember, critical points are defined where x is 0, or like the equation itself, the slope formula is 0 or undefined. In other words, I want to set this equal to 0. And I just solve for x, and that's how I get the critical points. So how do I do this? I go 3x squared is equal to 12, x squared is equal to 4, x is equal to plus or minus 2. You have to remember plus or minus, or you'll probably get the, actually you will get the problem wrong. So these are the critical points. And now with this, we can actually start looking at a number line. We found the critical points to be here and here. I'm just going to choose two arbitrary points. We don't really have to know too much about it, just know that they're one's on the left and one's on the right. And notice that it separates this number line into three regions. You have this region right here, you have this region right here, and you have this region right here. With polynomials, we know that it's never going to change somewhere in the middle, because if it did change somewhere in the middle, it's going to be either local max or local min. So in other words, this whole section right here is going to stay either positive or negative, and we just want to find what sign it is in this interval. Similarly, we want to find what sign it is in this interval and what sign is in this interval. And if we can do that, for example, if this is plus and this is minus, a minus region and a plus region, we can actually see this is a, looking at this picture right here, this is a max, for example. This is an example. And then if this is a minus to a plus, this is a minimum. And then the other cases, if it's plus and plus, then it's a saddle or neither point. So we want to actually look at these three regions, pick a point in this region. If we can actually find the sign of that point, we can actually start defining these intervals as positive or negative. So I'm going to scroll out or zoom out. In other words, I want to find three test points. Probably 0, that's always easy. 3 is always, you probably want to choose the next smallest whole number. So in other words, test, so these are the test points. So test this, and test this. And whatever the sign is, we're just looking at the sign because we don't really care about the value. We just know that if it's positive, then we can define the whole region as positive. So plugging in 0 to the slope formula, we get negative 12. In other words, this is a minus region. Plugging in f prime of negative 3, it would be 3 times 9 minus 12. This is a positive value, so we can automatically define this as a positive region. And then similarly, 3 times 9 minus 12 is a positive region. This is a positive region. So now we can actually define these critical points. So this is the critical point, and this is the critical point. Since it moves from positive to negative, this is a max, right? Max. A local max. And since this is negative to positive, this is a local min. So I just found the extreme, or not, the extreme values, the local extreme values of this function. There's no absolute extreme values because it is defined on all values of x, and if you recall from cubic regions or cubic polynomials, it will go to infinity and negative infinity on both ends. It depends on what the sign of the leading term is, but that doesn't really matter too much because we know it's going to be only focused on the interior region, especially with a polynomial without a specific region they give us. But all in all, local max at minus 2, or x equals minus 2, and then local min at x equals 2. And that's it. We just finished this problem using the first derivative test, only the first derivative test. And that's it for this example.